Good morning guys, and welcome to today's worked exam answer video. Today I've chosen to have a look at a similar question in some respects to the transition metal question I did at the start of this week. In some respects it's also different, and I did that to, I guess, kind of show another angle as to what they might ask about heterogeneous catalysis. So the example that I did earlier in the week was looking at how vanadium oxide, or vanadium 5 oxide, can be used in the contact process because vanadium exists as differing oxidation states. This is a slightly different way that heterogeneous catalysis can work. So a heterogeneous catalyst can also be kind of used as a surface, as a solid surface usually, on which gaseous reactants can temporarily adsorb onto, and by doing that we lower the activation energy for a few reasons, and then reactions will occur, the products will desorb, and that is an alternative I guess reaction pathway that a heterogeneous catalyst can make use of. Now, we've met a really good example of this in year 12, which was in the catalytic converters in cars. So looking at how some of the harmful gases produced when we combust the fuel that our cars run on can be reacted to make them less dangerous when they leave our exhaust pipes. So changing carbon monoxide and nitrogen monoxide into nitrogen and CO2, for example. That used platinum or rhodium or iridium, for example, as our transition metal catalyst, and that will be the surface. The gases will then adsorb onto those metals, reactions will happen, products will desorb, leave the exhaust, and we talked a little bit about the ceramic support that was needed, which again it's asking about here in terms of why we're going to want to use a ceramic support in that example. We also need to know a little bit about kind of catalyst poisoning, when this is the way in which the catalyst works as well. So lead found to poison the catalyst, and we now have unleaded petrol, unleaded diesel, because if we had the lead within the diesel or the petrol, then that would stop our heterogeneous catalyst from working, our catalytic converter wouldn't work, we would be emitting far more harmful emissions. So we're going to be asked again to define the term heterogeneous, which I know I did earlier in the week, but we've also got a new definition in terms of active sites, and then the rest of the question is a little bit different from what we had a look at earlier. So yeah, good to see a range of different things that you might get asked. And as I said earlier in the week, transition metals is a topic that you will be coming on to soon. It's very kind of labour intensive as it comes to learning and memorising equations and things, so hopefully having more videos of how that then it gets applied will be useful. So step 1, explain the terms heterogeneous and active sites as applied to a catalyst. Step 2, give 2 reasons why a ceramic support is used for the catalyst in catalytic converters in cars. Point 3, explain how lead will poison the catalyst. So again, fairly straightforward to see where we're going to pick the marks up here, but anyway, let's get cracking. So heterogeneous, as I said in the earlier video, I also couldn't spell then and I can't spell now. So heterogeneous is referring to the phase that the catalyst is in relation to the reactants. Homogeneous would mean that the catalyst is in the same phase, where phase is just state of matter, just a bit of a fancier term. Heterogeneous will be when the catalyst is in a different phase to the reactants. And in this case, we're thinking about having a solid catalyst and gaseous reactants. And then we've also got to define active sites. So I briefly mentioned before this idea of the the reactant gases adsorbing onto the surface of the catalyst. The places in which that happens can be called active sites, and I know that that's probably a word that we associate with enzymes in terms of that lock and key mechanism, and I guess it is sort of similar to that, but we're thinking about the places on the surface of the catalyst, the platinum catalyst in this example, where the reactant gases can adsorb onto. I think I'll just word it exactly as I just said it. The places on the catalyst's surface where the reactants adsorb. Okay, so I mentioned this word adsorbing now, and I am saying adsorbing, so ad-sorbing, not absorbing with a B. So the reactant gases will adsorb onto the catalyst surface, and that just means like we're temporarily binding them onto the surface. So we don't want that binding to be too kind of strong, because then once we've made the products, we're not going to get the products leaving the surface of the catalyst. Equally, we don't want the adsorption to be too weak, because then we won't have the reactant gases held in place and we won't benefit from having the alternative reaction pathway, which brings a lower activation energy. So the first step is we've got to get the reactants to adsorb on. The second step is that then the reaction will occur between other gases passing over the catalyst while we have some of the reactants adsorbed onto the surface. And by having the gases adsorbed onto the surface, we are effectively increasing the concentration of that particular gas in that particular area, because obviously gases will be normally moving around quite rapidly in all directions with plenty of energy, whereas if we're temporarily sticking them, for want of a better word, onto the surface of the catalyst, then they're all there ready and waiting to have other particles collide with them. So then other gas particles collide with them, and then we get that reaction occurring. So by sticking them to the catalyst surface, or them being adsorbed onto the catalyst surface, we are increasing the number of successful collisions, and we will also be having those adsorbed particles held in the correct orientation for successful collisions as well. And if we've got more successful collisions per second, we have a faster rate of reaction, and that's exactly what catalysts do. They increase the rate of a reaction. The other thing that happens when the reactants adsorb onto the surface is, because they're forming those kind of attractions with the catalyst's surface temporarily, the bonds that exist within those reactant molecules will get weakened. So if those bonds are weaker, we have to put less energy in to break them. So essentially we're bringing the activation energy down. Less energy needs to go into breaking the bonds, so it will be easier to break the bonds in the reactant gases, and then we can undergo the reaction and make the products. So that's kind of how this method of catalysis works. So we've got reactants coming in, adsorb onto the surface, lots of particles in the same space, weaker bonds between those particles, other gas particles come and collide, reaction occurs, products will then desorb off of the catalyst surface. Now, in terms of the ceramic support, which is the next part of the question, the first advantage of using a ceramic support is that we have an increased surface area. And if we have an increased surface area, then we've got more space for kind of adsorption of the reactant gases onto the platinum metal, and it also means that we need to use less of the platinum metal. We can kind of use a nice fine powder, and then we can distribute it over the ceramic support. We get a greater surface area, we've used less platinum in total, and that's a good thing because platinum is expensive because it's a rare earth metal. So yeah, that's the other benefit. Reduces the amount of platinum metal required, and then which reduces cost as platinum is expensive. And when they first started fitting catalytic converters onto cars, people would go around stealing them because of the platinum and the value that the platinum has. So that was a bit of an issue. Anyway, so that's why we've got our ceramic support. And then the final part of this question is explaining how lead will go about poisoning the catalyst. Now, knowing a little bit more about how the heterogeneous catalysis works is important for us to be able to answer this part of the question. So that's why I just briefly explained how we get the adsorption and the lower activation energy and the desorption, because we have the lead taking the spaces that the gaseous reactants would take. So essentially the lead will block the active sites, which again is similar to what we've learned about enzymes in terms of competitive inhibition, which you may or may not remember depending on if you've done A-level biology or not. But that's what happens here. The lead will poison the catalyst because it'll block the active site, and if the lead is blocking the active site, then the reactant gases can't adsorb on. You won't have weakened bonds, so you won't have a lowered activation energy, so the reaction is not going to get sped up, and the lead will actually bind irreversibly to the active sites. So as soon as you've then got all of those active sites filled up with lead, then your catalyst is rendered completely useless. So that's what we need to explain here. So the lead will bind to the active sites on the catalyst's surface, which blocks them. I'll put a full stop there. As the lead binds irreversibly, this then stops the reactants from adsorbing and thus the catalyst is rendered completely ineffective. There'd be no point in having it there at that point. Now, there are a couple of other questions that I've seen over the years whereby they've asked kind of how we can reduce the likelihood of catalyst poisoning. And to do that, we need to know exactly what is in the substance that is going to be kind of in contact with the catalyst. So in this example, in terms of the petrol and the diesel, knowing what is in the petrol and the diesel kind of in full will enable us to go, oh, actually, no, that's an impurity. We've got to get rid of that because that impurity is likely to then block the active sites on our catalyst. So having the most pure reactants and removing any impurities is going to reduce the likelihood that we get poisoning of the catalyst. That isn't a specific example you need to be aware of, but it is a really good relevant example. But anything that acts as a poison for a heterogeneous catalyst will be doing the exact same thing. The impurity will bind to the active sites on the catalyst surface, which will block them, and that will bind irreversibly, so then the reactants can't adsorb, and thus catalyst may as well not be there. Okay, so that's another 7 marker done. Again, possibly wouldn't be 7 marks in today's kind of papers, but we'd certainly be looking at sort of, I'd say 5 minimum for a question like that, which is still pretty good considering, you know, we haven't had to really state too much. We haven't had to do a lot of kind of application, understanding it, as I've said, inorganic, very factual. But if any of the facts that I've given there are unclear in any way, or you want to ask any questions or show me some similar questions to have a look at, please do get in touch. And yeah, wish you all a wonderful day, guys. Thank you.